From our earlier discussion, we learned that simple comparisons between two groups of people are not the right way to infer causal relationships. But unfortunately, it's common to see simple comparisons being gainfully employed in argumentation as evidence of causal effects. The problem with this again refers back to the ceteris paribus condition, or lack thereof. Other things must be equal. Comparisons of people with treatment and without treatment have to be apples to apples, otherwise, we have a selection bias problem. In the controlled experiment, we claimed equivalence between our control group and our treatment group, because our subjects were engineered to be identical, which meant that there was no difference in the average pre-treatment outcome between the treatment group and the control group. And this meant no selection bias. We wanted to claim something similar in our health insurance example. We wanted to claim that people in the control group and treatment group are near identical. The next causal inference technique we will learn effectively eliminates selection bias, and it's called randomized experiments. This is the graphic that's going to delineate our progress for us. As you can see, the first causal inference technique in our toolbox is going to be randomized experiments. And there's going to be 4 more techniques after that, which will complete our toolbox. Let's do some reviewing from the earlier module. Remember that to ensure a bivariate causal relationship between the treatment variable and the outcome variable, we wanted to fix everything but the treatment status as constant and equal. But we noted that the people that are already enrolled in health insurance are different than those who are not enrolled in health insurance in ways besides the fact that one group has enrolled in health insurance and the other has not. For one, the insured are healthier for all sorts of reasons, including, perhaps, the causal effect of insurance. But the insured are also healthier because they are more educated and wealthy, among other things. These unobserved variables that are not held constant to ensure ceteris paribus are called confounders. They are what cause apples to oranges comparisons and therefore selection bias. So how should we make apples to apples comparisons between the insured and the uninsured? Well, one way is try to make the blend of people in the treatment and control group very similar, which is exactly what a randomized experiment tries to accomplish through random assignment. The logistics of a randomized experiment, sometimes called a randomized trial, can be complex depending on the experimental design, but the logic is simple. To study the effects of health insurance in a randomized experiment, we first randomly sample a large number of people who are currently uninsured. Then we randomly assign about half of the people in our sample to the treatment group, and provide health insurance to everyone in the treatment group. The other half of the people in our sample that are not assigned to the treatment group, get assigned to the control group, and continue to be without health insurance. We wait for some period of time so that the effect of health insurance kicks in. Then, we measure the health levels of the people in the treatment group and the control group and compare the two. Any difference that is measured between control group and treatment group reflects the treatment effect or the impact of insurance on health level. Why? Because random assignment makes the group comparison ceteris paribus. Groups insured and uninsured by random assignment differ only in their insurance status and any consequences that follow from it. Why does random assignment do this? Because random assignment is random. It's not biased towards putting any person into treatment group over the control group. And we don't give people a chance to self-select themselves into a particular group. We should quickly note here that random assignment of subjects to treatment and control group may not produce two groups that are near equivalent. And this is precisely due to chance. We might get unlucky and get two groups of people who are not alike. The cure to mitigate the effects of chance is larger sample size. You can imagine a random assignment regime of hundreds if not thousands of people to each group, so that probabilistically the two groups will be similar. This fact is mathematically guaranteed by a property called the law of large numbers. The best way to learn causal inference techniques is by seeing how they are used in real life. Let's head right into an example of a randomized experiment with the Perry Preschool Project, which was carried out for 5 years from 1962 to 1967, which provided preschool education to at-risk African American children living in Ypsilanti, Michigan. 123 children were randomly sampled from the population and about half of that were randomly assigned to enter the Perry Preschool program. And the other half continued to be without preschool education. The program lasted about 30 weeks. Researchers then contacted the same subjects in follow-up surveys when they turned ages 14, 15, 19, 27, and 40 to measure the causal effect of preschool education on economic outcomes. This table is the main result coming from the most recent follow-up study done in 2005. As you can see, the treatment group has measured higher in cognitive skills, university enrollment, and employment status. Incarceration rates and the percentage of people on welfare are far much lower in the treatment group than the control group. The column indicating p-values is going to indicate the statistical significance of these findings. A rule of thumb is that if the p-values are less than 5%, we can reasonably say that there is indeed a treatment effect of enrolling in the peri-preschool program, and it's not just due to chance from sampling error. This is the conclusion from the authors of the study. Because children were randomly assigned to the program or a control group, differences in outcomes are probably attributable to program status. The data shows strong advantages for the treatment group in terms of higher lifetime earnings and lower criminal activity. How about another example? But this one from more than 160 years ago. In 1854, there was a very serious cholera epidemic in London, which prompted the English physician John Snow to investigate the cause. He suspected that water contamination caused by the sewage release in the Thames River was the cause for the outbreak, but he needed evidence. To prove this using a randomized experiment, he would have had to randomly assign people to separate groups, and force them to drink water from varying water suppliers, and subsequently measure the frequencies of cholera deaths in each group. But Snow did not do this. Instead, he collected observational data on which addresses got their water from which water companies, and which addresses had cholera deaths. For Snow, this data was super useful, because the data reflected a process which closely replicated an actual randomized experiment. Snow noted that Londoners received water from water companies in a near-random way, so it was almost as if people were randomly assigned to drink contaminated water, versus non-contaminated water. This was the main finding from Snow's study, which proved that water source was the cause of the cholera epidemic in London. There were 3 major water companies in London. And Snow associated each company and its water supply with an address. Then he noted whether people had died in that address. And it turned out that Southwark and Vauxhall supplied water that caused the most cholera deaths, because Southwark and Vauxhall had been pumping water from the part of the Thames River that was near the main sewage discharge for London. Contrast that to the Lambeth Company, which drew its water far north from the discharge. Hence, its water was less contaminated and caused less cholera-related deaths. The lesson from Snow's study is that when we cannot do a randomized experiment, the next best thing is to find situations that mimic randomized experiments. We call these quasi-experiments, or natural experiments, where there is a source of randomization that is as if randomly assigned, and not the result of an explicit randomized experiment. Before we move on from the discussion of randomized experiments, we'll note some potential downsides to randomized experiments. First, the Hawthorne effect, where subjects in our study react to being part of an experiment. Therefore their outcomes may become biased. Second, the spillover effect. Sometimes the control group becomes affected by the existence of a treatment group nearby, and therefore receive the treatment partially. In the peri-preschool project, you can imagine children assigned to the control group, interacting with their friends who are in the treatment group and therefore absorbing some of the treatment effect that only those in the treatment group should be receiving. Third, the heterogeneous effect. Meaning that the same experiment may have different effects across contexts and target populations. The peri-preschool program focused on African American children of ages 3 and 4, so it's conceivable that this program might not have the same magnitude of treatment effect on children of other countries or races. Fourth, compliance issues. It's usually the case that not all subjects in the treatment group end up participating in the program, and if they do participate, some subjects might drop out of the study. And lastly, ethics. Because the rationale for conducting a randomized experiment is based on the fact that researchers are genuinely uncertain over the benefits of the treatment. What we've covered about randomized experiments, while brief, covers most of the core ideas. If you want to learn more about randomized experiments, these are the resources I recommend.